So this session is on material design. So I therefore prepared my talk piecing together different results from projects that are ongoing together with my two students, Sever and Philip, who are also sitting in the audience now. Then other projects done in collaboration with friends and colleagues, for instance, Domenico Di Sante in Würzburg, the people in Vienna, Alessandro and Carsten. Then I will present towards the end something on transition metal decalcogenides done with Tim and Rosa in our German research collaboration, and also with with Jan Budic and Björn Trautzepp. So essentially I will be elaborating on whether we can always interpret the lifting of orbitals in many body systems as a renormalization of single particle Hamiltonian parameters, or if there is more to that. And things can be already understood by making the example of the nickel heterostructures. So I'm talking about the pre-D9 nickel age of superconductivity that Harald Wang yesterday presented. So here we have more D7 to D9 physics, and we are talking about the splitting between two orbitals, two EG orbitals, a planar one and an out of plane. And this is something, of course, that many of you guys have been also looking at. So the effect of many body correlations onto this split multiplet. And essentially we interpret things in terms of a very simple renormalization of the DFT crystal field that I show here by means of the real part of the self-energy at zero frequency. And we can typically have just two situations, two opposite situations. One in which the crystal field splitting by DFT is increased by the self-energy correction, and instead a situation in which the many body correlation oppose the tendency of the original tendency of DFT. So the first, essentially, the first example will be covered in the first part of my talk by looking at oxide heterostructures. And instead that we will see, I will present one example of the second scenario where when I'll be discussing about correlated topological insulators and twisted bilayer transition metal decalcogenides. So the question will be whether we can always use this very simple equation, single particle equation that you see down there. So you have seen already in the previous talk by Divine how still active this field is. Heterostructure give possibilities to realize phases that are not present in the bulk constituents. In particular, by reducing the thickness, we have seen the example of the manganites in Divine's talk. Instead, I will be also discussing this thickness-induced metal insulator transitions, but in vanadium and in iridium compounds. Either we discuss this in terms of the EG manifold in case of late transition metal oxides. The first example that I will be showing is instead in the T2G case, where the breaking of the translational invariance along Z makes the otherwise degenerate, in the bulk degenerate T2G orbitals differentiate and pushes up in energy the out of plane orbitals. So this is what happens in the good old friend strontium vanadate. In this case, you see an experiment, the results of an experiment of the Japanese group who have shown how by going from the bulk case, or building a thick strontium vanadate film on top of strontium titanate and reducing this n, the number of layers, you lose progressively, but well, actually not progressively, abruptly between 3 and 2, the quasi-particle peak of strontium vanadate. And the question was, what is the mechanism behind this? And it's exactly this enhancement of the crystal field splitting that I was mentioning before. So that's what DFT tells us. Imagine here you have your slab. Just take the example of n equal 2. So the you see there is still a metallic, this is still a metallic system, but you already see the differentiation between XY and YZ and XZ. The blue orbitals start to be split and develop some quantum well features. And the question is whether DMFT can finish the job and get the job done and make it insulating. The answer is yes. In this case, we have studied exactly this, this thickness-dependent transition. You see very clearly that the DMFT enhances this crystal field splitting by making the YZ and XZ orbitals completely empty. And so that's this orbital polarization occurring at the interface is less pronounced in the second layer, so in the interface layer. And since this happens via a very abrupt dependence, you see here depicted on the right hand side the correction to the crystal field splitting as a function of the interaction parameter. And contrary to what a Hartree-Fock calculation would tell you, so in Hartree, you would get the real part of the safe energy, which is linear in U and linear in N. DMFT instead gives you a highly non-linear kind of first order behavior, making this object very sensitive to small changes. So for instance, in our DMFT calculation, we immediately got a metal at n equal 3. Pressure, strain, temperature were all going towards metallization, driving the system to metallization. So in any case, this mechanism that I've shown at the beginning is here really very clear and active. The story, however, on strontium vanadate thin film is not over. Recent experiments here done in Würzburg in the group of Ralf Claesen showed that first they looked at the bare vanadium strontium vanadate film termination, and they discovered a very strong they measured a very strong tendency towards oxidation, over-oxidation. So in particular, they see that the vanadium O2 termination that they get in pulse laser deposition gets modified by a square root 2 oxygen reconstruction. So every second vanadium, you get an oxygen that completes the octahedron. And this, of course, gives you a D0 contribution. And to get rid of that, they kept the system with strontium titanate again, and restoring the D1 vanadium nominal valence. And to their very big surprise, they push this thickness induced transition to much larger values. So now this X is the N of the Japanese experiment, and it's no longer 2, but it's around 6, 7. So the film with even with n equals 6 are still insulating, which is very surprising in some sense, because in DFT plus DFT, at least you clearly see that at these thicknesses, you are extremely close to bulk strontium vanadate. Just to give you an idea how sensitive things are in this, when you have this enhancement of the crystal field splitting that can be of first order, I show you two calculations. The left one is on strontium O termination. And here the crystal field splitting by DFT is negative. And the sign of the crystal field splitting in DFT is very important because it determines the in which direction the enhancement of the MFT goes. So here, if you do the MFT, you get that the XZ and YZ orbitals go up and get emptied. Whereas if you do it here in an ideal vanadium O2 termination, you get not a huge difference in the band structure. So you still get that gamma in XY pocket, but the crystal field splitting has changed its sign. And in this case, DMFT, which you see in the bottom panel, would empty the XY orbital immediately. So we are working with our friends in Vienna to see whether we can understand this surprising enhancement of the critical thickness in terms of very subtle structural relaxation effects that change this crystal field splitting and then the response of the MFT. Thickness dependent transition happens also in more complex oxides. Here I show the case of the iridium films. Of course, here we have also a spin orbit coupling that we have to take into account. The Claesen group realized these films and they are able to, by reducing the thickness, to get rid of the metallic weight at the Fermi level. Here, concomitantly, and we can describe this very nicely with the FT plus U, concomitantly you get a change of the structure. So in some sense, when you make the film, the iridium film thinner, you see that the tiltings of the octahedra present in 113 iridium go away. So strontium titanate is a tilting killer in this sense. And we think that concomitantly there is also magnetic fluctuations changing dramatically that are also either responsible or are an effect of this consequence of this metal insulator transition. Essentially, you can think of this as a very effective way of going from the 214 bulk in the thin case to a 113 bulk iridium in the thick limit, as it has been described, for instance, in DMFT by Chris Naule here. And the 214 is indeed insulating and magnetic, and the 113 is a correlated metal. This interplay between spin orbit, structural distortion, and magnetism is also common to many other late transition metal oxides, 5D in particular. And you can see this afternoon, if you are interested, something more on that, but on the osmates by Severin, his poster. Here, it's also interesting to ask what happens to the termination. Of course, since you're looking at such thin films, of course, the termination is very important. And here, what happens is not what was observed in the vanadium case, namely a termination conservation, because in laser pulse deposition, they essentially shoot entire unit cells. So if your strontium titanate is terminated with titanium O2, you should end up with iridium O2. Here instead, oxidation of iridium O2 leads to iridium O3, which is very prone to evaporate. And so the actual termination is the strontium O termination, which is the one we usually naively, without thinking, take into account in the FT calculations. Here is this is due to this termination conversion, something that is very well known in the rutanate case, where there is also this doubling of the rate oscillation leading to a termination conversion. And we have checked with Domenico that indeed experiments are much better described if we use this termination rather than the nominal one, or the one that you would get in the case of the conservation. Good. So, so far I've discussed these two the case of the enhancement of the crystal field splitting, when do we get the other possibility, namely, when do we get a opposing effect of the many-body correction to the crystal field? And this is still taking our initial example of the nickel heterostructures. This is obtained when you raise the filling from 1 electron in the EGs to 2 electrons, so when you go to D8, because in that case, the Hund's coupling starts to become much stronger and wants to create a high spin triplet Mott insulator in the ground state. And so it effectively reduces the splitting of the DFT. So to study that, I considered a model that in its origin is completely uncorrelated. So semiconductor, mercury telluride, the BHZ model is a 2-orbital model, half-filled, 2 orbitals here and 2 electrons. So everything is described by these 2x2 blocks, and in particular by this D vector that is written in the space of the 2x2 Pauli matrices in the orbitals. And the way this D vector winds around the Brillouin zone tells you whether you have a so-called non-inverted band structure. Imagine your M is very large. So in this case, you don't wind around the unit sphere. So that's a Chern number equal 0. Whereas if M is smaller than 2, then the D vector will cover once the unit sphere, and you have a so-called inverted band structure in which the s orbital in conduction at the gamma point starts to have a little bit of weight in valence. So this topological phase transition happens as a function of M in a very smooth way without interaction, and our motivation was whether we can trigger this by means of electronic correlation with the effect that I've described before. So that's one of the most general ways of writing a 2x2 a 2-orbital Coulomb interaction, in this case without spin flip and per Opping terms. It's not decisive here. The only thing that I want you to focus on is this opposing tendency of the many-body correction. So we really get this high spin here. Everything can be described by this 0th order correction that I've discussed so far. And the first consequence of this is indeed that we go from the trivial band insulator, we can go into the quantum spin-Hall phase, into the topological insulating phase, not by decreasing M as for U equals 0, but increasing the Coulomb interaction. So this is a schematic phase diagram based on our DMFT results solved by our CT Hybe Monte Carlo. And essentially, this is already a nice result that you can induce topological phases by increasing U, but there is more to that. You see these colors. So in particular, in the quantum spin-Hall phase, you see a very strong change of color. And this color is indeed the thing that is more to our single particle renormalization. So look at the, let's look at the self-energy really, not just this, not just take this 0 value and 0 frequency value. So if we do that, we distinguish very clearly between Hartree-Fock-like self-energies that are really flat, and where, so for instance, here in this part of the phase diagram, where we really can discuss things in terms of renormalization of our M orbital splitting parameter, right? Thank you. But if we go deep into this more correlated regime, then we start to observe a very strong and pronounced frequency dependence. So the correction is no longer a static object, and the color is exactly proportional to this many-body quantity, many-body nature. So the system is actually trying to go to connect a trivial band insulator, which is always Hartree-Fock-like, here with something that is also Hartree-Fock-like. So this transition is smooth and second order as for u equals 0, whereas here the topological phase transition happens with a gap that abruptly gets inverted. So a jump in the gap inversion, similarly to other cases also discussed by McDonald. So the consequence is very interesting. Namely, you get a semi-metal if you cross the band touching point for small u, whereas if you go above this quantum 3 critical point, so the end of a first order line, you get the end of a second order line, you get the chair number change, or the Z2 invariant that change, but not a semi-metallic bulk phase. So this is also translatable to the Kane-Melle language. Here the orbital splitting is a Semenoff mass between A and B, which is here. I still call it M, contrary to the original notation by Kane-Melle. This term breaks inversion symmetry and brings you to a trivial phase after beyond a critical value. So you get this typical onion in Rashba versus Semenoff mass diagram. And the interaction that you would introduce here is simpler. It's just a typical Hubbard single orbital interaction, but it does the same job. So it suppresses the staggered potential that you can start from and induces a topological phase transition here in this DMFT phase diagram as well. Why did I bring the Kane-Melle model? Well, the point is that we have in mind a very specific material realization of all that. And this is indeed transition metal decalcogenides, tantalum diselenide. This is a system that in the monolayer 1T phase has a so-called Star of David reconstruction. Charge density wave is a commensurate charge density wave instability. And you see from the top here, the tantalum atoms, they form these stars. And the nice thing is that you can bilayer or tri-layer them. And by doing that, you change very clearly the band structure of the Star of David phase. This is shown down here. So that's the monolayer. It has a very nicely isolated and super flat tantalum D band out of this. Despite the complication of the unit cell, somehow you have a very simple low energy structure. And if you bilayer this by making the stacking such that the top layer, the Star of David in the top layer sit exactly in the middle of 3 Star of David in the bottom, then you do something that you can sort of describe like the opposite that you do in bilayer, in twisted bilayer graphene. Because now you set these very localized MOT electrons, you set them free to have an honeycomb dispersion. So you see, you open now up a nice honeycomb dispersion when you bilayer these things, and you can even twist this by 180 degrees, for instance, and open a Semenoff mass, so a gap because of the breaking of inversion symmetry that you have in these 180 twisted bilayers. That's a very interesting way of working with these Dirac fermions. Here you break the inversion symmetry, then the D6 symmetry of the graphene layer, in that you not only have you essentially have a breaking of the sublattice equivalence. Therefore, you not only generate the typical Kane-Melle SOC spin orbit coupling term, but you also get this so-called spin valley term, in which you have only the spin and the KK prime polymatrix, which deforms the onion this way. You see here, it breaks the symmetry and you lose progressively this quantum spinol phase. The nice thing, however, is that we can sweep through the onion very effectively by applying an electric field along Z in this case. So we estimate the U. In these bilayers, we get something that is 4 to 5 times the hopping integral. So the system is really strongly correlated. It sits close to this 3 critical point. And this is realized in this very beautiful experiment by Mike Cromie. The only thing is that the stacking is slightly different. It's not this perfect honeycomb stacking, but rather a so-called AC stacking, which the Star of Davids are sitting on top of each other. Our stacking is a metastable phase, so we are figuring out whether we can also get from experiments signals of our stacking. So the message, however, is that in this phase diagram, tantalum dicyanide bilayers are sitting here, and we can operate through these transitions by applying electric field in a very efficient way. So to conclude, I showed you the different possibilities that you have in heterostructures, in oxide heterostructures, in particular thickness-induced metal insulated transitions, and in the end, this local criticality in the correlated topological insulators that can be realized by bilayers of transition metal decalcogenides. Thank you very much.
Okay, we have time for a few questions. So I would like to start with one. So you showed these beautiful DMFT calculations with few different transition metals in a heterostructure, right?
Yeah.
So was there, I know asking about double counting is never kind, but was there anything particularly troublesome about double counting in these calculations, or did
right.
Resolve?
Thank you for these questions. So in principle, actually, here you should take into account, if you want, orbital. I mean, in the moment in which you are splitting two orbitals, you should wonder whether you should put a double count in there. And in principle, if you use an all-electron DFT code, you should do it, because the radial part for the different orbit, the radial part of the wave function would be different. Here we are using VASP, where there is no such, I mean, the radial part would be different. They would be the same among them, so we can avoid putting an orbital dependent double counting. But I mean, this is a subtle issue, so it depends. Indeed, also how you, it depends what one considers as bare, you know. I showed here DFT crystal field splitting, but this is not really the bare one. So here you get oxygen contribution, not only the Madelung potential, but also this radial contribution of the wave function. So that also depends on how you extract that.
Thank you. And yes, please.
For the STO, SVO, do you see any evidence for titanium states and might find some charge transfer between vanadium and titanium?
Yeah. Could you hear the question?
Maybe please repeat it.
For the STO, SVO,
yeah.
Here, do you see any evidence of charge transfer? Did you ask
Yes.
near the interface?
Yes, yes. We get a little bit of titanium states. Let's see. In experiments, they don't. I mean, it's very hard, you know, to go and check whether really the titanium 4+ signal is there. So in the DMFT calculation, we definitely get a little bit of titanium. I mean, yeah, that's the short answer. Maybe we can discuss later some details.
Maybe one more quick question. Well, it is lunchtime here, so I see that
yeah.
we have to leave. So let us thank Giorgio once again.